Okay, hello. Glad to see the few of you as always. So thank you for that. Have made it to the live stream. Very much appreciated. Week 12. So not just a huge amount of the semester left, which is good news. Um, we add arrays. We are doing arrays this week, and that means that you can forge ahead at this point and do most of the second project with what we talk about this week. There will be one aspect of the second project that we won't have covered yet, which is dynamic memory. But all of the algorithms don't change. Most of the project can be written as of the things we talk about this week. Anyway, so just heads up about that. I can kind of detect, and other teachers I know are also kind of detecting that people's energy is flagging at this point of the semester. So we just need to kind of buckle up and focus and get ourselves through the end of the semester. I hope. I suffer from the same fatigue, doing the better part of 8 hours of live streaming every week. Wears me down too, so I get it. Hi, Amberwolf. Nice to see you. So yeah, we're all experiencing it. But whatever it is you got to do to sort of maintain your focus, the one thing I would say is try not to get in bad habits, because it's hard to get out of bad habits. Even with schoolwork as an example. So one class had trouble with the discussion last week because I guess basically nobody read the instructions for the discussion. And one student wrote a thing that didn't have anything to do with what I was asking, really. And then everyone else just kind of did the same thing. So I think that's just a matter of focus. So break yourselves out of that and finish strong. We do a lot of work in classes like this, and it would be a bummer to kind of go limping into the end of the semester. So if your focus is still going strong, then please keep that. Hopefully, I don't do anything to interrupt that. But if you kind of need just whatever it is that you do to convince yourself to focus, work hard, do good work, and just keep those good habits, hopefully you can do that. All right, week 12. I don't know that we have a super long live stream today, so I might poke around in the third project. But anyway, here's where we're at. This is the week of November 7th. So we add arrays, and with arrays, we have the ability to implement most of what Project 3 asks of us. And then we don't have a whole lot more. I will show you that for your class, and for those of you taking P&A 2 at the same time, or some other kind of workload heavy class. Week 14, let me just show you real quick what week 14 looks like. Week 14 has no assignments for you. So that's the week of Thanksgiving. I don't do this in my other classes, but we have never had a moment to stop and just me kind of review what we've done up to that point. So if that helps your energy levels, sort of just be on the lookout. 2 weeks from now, we have a week where all I do is a review. You don't have a discussion. You don't have homework. You don't have a lab, although there will be that project hanging out there. So you do get a small break here in a couple of weeks. All right, so we're in week 12. And then notice the second project is due on December 11th, which is the Sunday before the last week of class. So I don't do finals. What I do instead is I deliver content to you, which I hope you find more valuable than spending the week studying for and taking an exam. We will talk about floating point and do a normal week around how do you do floating point in binary that last week of the semester. Okay, so that's kind of what's coming up. Project 2, did I put Project 3 on the agenda? I didn't. Okay. Anyway, I'll talk about it today, but start getting that somewhere into your workflow that Project 2 is out there, and after this week we are tooled to do almost all of it. Okay, so before I go switch over and just do code stuff, so we are continuing addressing modes And I guess this is the time when I had already, the second item on my agenda. So I'll go ahead and say this part about addressing modes, which is where one of the classes in Piazza kind of got off the rails. Addressing modes is talking about accessing memory. It's not talking about writing assembly instructions. I mean, you do have to write assembly instructions to access memory in assembly, but addressing modes is how do we access memory? And most high-level languages allow different ways of accessing memory. And by accessing memory, hopefully everyone knows what I mean by that is RAM. And what I mean by that sort of at a higher level is how do I get at the data that is my program? Well, address modes are the way that we do that. We love direct addressing because that's the simple and obvious way of getting at data. We use a fair amount of indirect addressing, which if you are in the C world, that looks like a pointer. In assembly language, we talk specifically about the addresses of things that we use to get at the data. So this week we are adding, I should have put a little separator after this one. This week we are adding the array accessing, the addressing modes associated with arrays. So we will do indexed addressing and scaled indexed addressing. I find this interesting because it's one of those areas where I appreciate a small thing that high-level languages do for me. So hopefully everyone has done some kind of creating an array, populating an array, iterating an array, accessing the individual elements of an array. The one thing that you don't have to do in high-level programming is worry yourself a ton about the finer points of indexed and scaled indexed addressing, because a lot of the more difficult parts of indexing arrays are being handled by the languages themselves. But in assembly, we have to do everything by brute force. But assembly, x86 assembly, does allow two different forms of indexing to get at data that's being stored in an array. Okay, so I jumped ahead of myself. So when we're talking about addressing modes, we're talking about how do we get at data in memory. That's it. We're not talking about can you use assembly instructions in a programming language. That completely irrelevant, which you could easily find just by Googling addressing modes x86 or addressing modes, probably even without the x86. So anyway, that's part of the sort of the focus issue is read the discussion prompt, please, and be thoughtful about your responses. One of the sections has already got a few people started up this week's discussion, and they started up good. So if that's your group and you go and you find that there's already some posts in your discussion, those people did good work already. So you have a good model to follow. Okay, anyway, that's that rant. So the other thing is the week 11 lab. So 90%, of course, of everybody does perfect every week. But I do like to point out where I see patterns that I think are probably just semester fatigue, because in the fall we really don't get much for breaks. So it appeared that a lot of people this week, maybe you compiled your code just to see if it compiled, but you didn't actually run it to see if it actually performed as expected. So if you hadn't noticed it before, I design every lab in this course pretty much to be an interactive tool. So you implement and you see the assembly instructions, but then you run the program and you interact with it, and you can use the lab programs to actually learn the thing that we're trying to learn that week. So many of you do that, but not everyone does that. So the part of the point is to get a running program that then I can go input data into and view the results on the screen and use that as an opportunity to learn whatever it is better. So anyway, there's a lot of sort of untested code. And if you got a comment from me about it, it's because when I do 50 plus of these things, it gets frustrating that the testing is being dumped on my shoulders. Now I realize it's my job to give you feedback, but I get no learning value from that. So it does sort of get to me a little bit that you have wasted a learning opportunity by dumping basically crap in my lap. So if that's you, I'm just sort of appealing to you to get your focus back and finish the semester strong. One of the common problems that I saw in the lab is that people weren't bothering themselves to think about the inputs. So we had int 8 inputs, int 16 inputs, and int 32 inputs. And I've talked about this before, and this is something that you want to carry forward in computer science and engineering. You want to test your systems with stresses or inputs on them that actually test the system. So as an example, several people had negative 99 to 99 as their input ranges last week. And the reason why you did that, no doubt, is because you just kind of quickly copied and pasted and I don't care and I'll just move on. But if I'm trying to test an int 32 input and I'm limited to values between negative 99 and 99, I don't actually know if your int 32 input handling even works. Because you might have made a mistake and you used get I8 in there, and I can't trigger any errors with being limited to that range. So I had to alter those people's code myself so that I could actually test your functions. You're welcome, because I gave you credit for those functions, even though technically I shouldn't have, because I couldn't test that they actually worked properly. So what's an appropriate size appropriate input for an int 32 is negative 2 gajillion and something up to positive 2 gajillion and something, whatever it is. You can look it up online. Or at least something that is bigger on either end than an int 16 could be. So int 16 only goes down to negative 32,768, which means that anything less than that would allow me to test an int 32. And int 16s only go up to 32,767, which means that anything greater than that would allow me to test the int 32 fully. Hopefully that makes sense. So negative 99 to 99 makes sense for int 8. It's terrible for int 16 because that doesn't prove that there's an int 16 functionality there. Int 16s need to go below negative 128 and go above 127 to fully test an int 16, and then the same. So that's what I mean by size appropriate ranges. If you got notes about that, I didn't take as many points away as probably I should have, because I couldn't actually test those two functions, which were 9 points apiece. But I edited your code for you and added the appropriate ranges for myself so that I could test that those two functions were properly implemented, and then I gave you credit for them. So anyway, those kinds of things, if you got comments, it's because that's frustrating for me when I know that you know how to do it. So always when you're out there as an engineer, don't not show your skills. If you have them, there's no reason to not show them. Although I realize that sometimes that means a little bit extra work. Okay, there's my rants. Yeah, so Amber Wolf in chat points out just because it compiles doesn't mean it works. Definitely true. There were a lot of people when the program printed. Not a lot, a few people when the program printed the data, there was a bunch of zeros in there, which should have been if the person had bothered themselves to run the program once. And you see zeros when you input numbers, you should have thought to yourself something's wrong. So anyway, I'm saying this to no one, to everyone who did it perfectly, and the people who didn't aren't going to bother to watch this anyway. So there's my rant. Sorry about that. 90% of you plus did great and perfect work, and you got hundreds for having done that. So sorry for, and thank you for indulging me in the rant. Yes, compiling isn't good enough. Compiling is for newbies. It is not for engineers. Compiling is for school kids, not for engineers. Compiling and then working as expected against good testing inputs is what engineers do, which many of you are already there in terms of being good engineers. So good on you. Okay. there's my rants. So for this week, we are doing indexed addressing mode. I think this is one of those weeks, which doesn't necessarily happen for all of us every week, but this is one of those weeks where we gain some, I think, instructive insight into some of the things that high-level languages are designed to do. And then also some insights into some of the limitations that high-level languages impose upon us. So we're talking about arrays, and we're talking about the two different ways that we can access the data inside of arrays. And for some reason, I used to find this difficult, and I guess just because I've repeated a bunch of times. But hopefully you walk away not thinking that this is all that difficult, even though the code can look nasty. Hopefully the concept won't be difficult. Okay, so readings, homework as always. The lab, I'm going to open it because I do want to go through it before we close out and make sure that there's no surprises in there for anybody. Okay, so here's the discussion. And again, sort of, I'm reading it to you guys who are watching the video and here in the live stream, and I don't need to read it to you because you can read it for yourself, but just in case someone watches the video later. So the prompt asks you to go see how arrays are done in different programming languages. So the great thing that one of the sections that has already started the discussion is doing, which is exactly what you would want to see because that's more value to you, is that 3 people have chosen 3 different languages to answer these prompts. So there's someone did, what does an array look like in the C language and how do you access elements? Another person did C++, another person did Go. There's a whole bunch of programming languages out there, so there's no need to do any duplication. In this discussion, it's a wasted opportunity for each of us as individuals to learn that one thing we go look up, but also to kind of get a survey of what do these array techniques look like across various languages. I personally think that it's very empowering is probably overstating it, but when you realize that so many of the high-level languages that people use have so much of their features in common, the idea that you would ever have to program in different languages becomes a non-issue because you realize, most of these popular languages are pretty much alike in so many ways that I doubt it would take me very long to figure out how to work productively in some new language that someone threw at me. So that's part of the reason why I do this, is so that you might walk away thinking that having to learn a new language is not that big a deal. You will recognize lots of the features. You'll know how to do many of the things based on your experience in other languages. That should be, I think, true this week in HLA, by the way. Okay. And then reminder, so homework lab discussion, as always, lab week 14, just so you know, gives us all a little bit of a break. I will still do what I do, but you guys won't have any work that week. Second project, I'm going to open it because I'm going to visit it today and get us hopefully started on doing the second project. Okay. We don't need any of that. So let me switch. And probably everyone will be very happy to know that I'm not drawing any pictures in this class. My PNA 1 people are going to have to watch me draw pictures, but you guys get a break from me drawing my terrible pictures. Did I switch? I did. Okay, so let me get myself set up. That's just to be sure I don't get any names out there. Okay, so we're going to do some basic array stuff, and it's different in HLA, and you immediately, once we start doing them, making arrays and accessing out the data inside of them, we realize that HLA has taken away something that we take for granted about arrays. Week 12. I don't want to be bothered with that. You know what? I should have saved this as week 12. Okay, so I'm going to create an array in HLA. It's not going to look all that exciting because it's basically the same thing that you're used to. So let's make an int 8 array of 5 elements, and we'll just leave it like that. So I'm going to start with the easy one that doesn't really expose the problem just yet. Okay, so here we go. Actually, let's pre-populate it, because if we pre-populate it, then instead of seeing zeros, we'll see actual data, and that will help us discover if we've caused ourselves any kind of a problem. So I'm just going to start by printing them out, and it's going to look the same as it always does, but something different is going on. We just won't see it yet. So we'll do element 0, numbers at 0, all looks the same so far, and I'm going to do all of them real quick, just manually like this. All right, no big surprises yet. Looks exactly the same as we would expect it to look. The creation, the declaration syntax is slightly different, but fairly trivial. 5 int 8s in an array, and then I'm going to pre-populate them with these values so that when we display things to the screen, instead of just allowing them to be zeros, which would make it difficult to detect problems, I'm going to put actual data. So here's one of those kind of making a smarter decision about the way you set up your code so that if you're going to use it to learn off of it, if I left it as zeros, it would be exceedingly difficult to detect errors. If I change it, however, into 10, 20, 30, 40, 50, then that, instead of seeing zeros, I should see 10, 20, 30, 40, 50. Oops, just do HLA test clear. What? Oh, I put an extra dot. Oh, I called it week 12. All right, so confirmation that arrays seem to work as they normally would in any other high-level programming language, but it turns out that if I do this, if I turn them into int16s, and let's go ahead and make them 20, 130, 140, 150. So not all of these values are bigger than int 8, but the 130, 140, 150 are bigger than int 8. So again, that's just to kind of make sure that I'm getting the sizes tested out somewhat correctly. So let's look at the data now if we do this. All right, so everything has just gone completely haywire in here. So what's going on? So I will tell you, and then I'll convert this to hex and see if that helps us understand what's going on any better. So it turns out that at the assembly level, the value in the square brackets is not the index like we think of the index being. That value in the square brackets is how many bytes, no matter what kind of data is in the array, that number in the square brackets is if I start at the beginning of the array, which we would call the base address of the array, which is represented by the label numbers. So if I start at the base address of the array and move how many bytes over from there do I want to move? So if I start at the base address of the array and I move 0 bytes over, I get the first value. It's the one literally at where the array address begins. This is why there is zero-based indexing in high-level languages, is because that's what that index actually represents, is the memory offset value from the beginning address of the array to the data that conceptually is being stored inside of it. So if I move 0 bytes over, I get the first value, and I did, get the 110. Okay, so all is fine and good so far. So the value that I consider to be at position 1 in the array goes completely haywire. So I'll see if anyone in chat has got warmed up enough that they can answer this question. So what I'm saying here is go to the base address that is numbers, go to the beginning of the array, move over 1 byte. Why does that go haywire? Goes by 2 bytes at a time. Nice one, Emberwolf. Because these values are 2 bytes per. So started going 0 over, I do get the first one, but then I have to move over 2 bytes to get the second one. So I'm going to go ahead and run it and see if that works. There's the 120. And then I get 120 again, oddly. Because I'm still 2 bytes over. Okay, so for the value at index 2 at the assembly level, we have to think, okay, how many bytes over is this third item? Four, good one. Emberwolf is on top of their game today. 4. So each one is 2 bytes over from the last one. So I'll go ahead and finish that thought. These values are not what we think of normally as the indexes. They are the byte offsets from the base of the array. So the last element is go to the base and then move over 8 bytes. So if I go to the base and then each one is 2 bytes, well, I have to pass over these 2. That's 2. I have to pass over 4 and then pass over 6 and then pass over 8. And if I pass over 8, that gets me finally to this last value that's in the array. Why did I press Control D? I don't know. That's right. So Emberwolf has already anticipated my next example, which is if I change those to int32s, would I have to go over 4 bytes at a time? And the answer is yes, I would. So good one. So there's all my values intact. Now let's make them 32-bit testable, right? So these values easily fit in 32 bits, but they don't fit in 16. So I can kind of avoid any misunderstandings by just putting 32-bit only style values in there, and that will help me test. No. So let me go back. So there's a good question from Druid. So why am I going over 2 bytes at a time? Because each element of the array is 2 bytes a pop. So the reason why we are computing these offsets in bytes is because that's how x86 does it. So when we are accessing memory stored as an array, we have to compute the offsets in byte values. So the reason why we're going 2 at a time is because each element is consuming 2 bytes of memory. Because each element, we have 5 int16s, which is a total of 10 bytes of memory being used. 2 bytes each, 5 of them is 10 bytes. So the 2 bytes is because each element is 2 bytes. Yeah, that's true. So Emberwell says this is, if you can keep it in your head that AL is 1 byte, AX is 2 bytes, EAX is 4 bytes, that is the same kind of mental gymnastics we have to do here. So let me put back my int32. All right, so if I make this an int32 array, 4 bytes per, which means that the array itself actually consumes 20 bytes of memory. This part HLA is handling for me, but when I go to access the things, I have to account for how big each element is. So the 0 offset still gets me to the first element, but then, as Emberwolf noted earlier, I got to move 4 bytes at a time. If I don't move the whole 4 bytes, then what I'm effectively doing is kind of grabbing from the middle of 2 different values, probably. So this one consumes 4 bytes. So to get to 99,120 here, I have to step over the 4 bytes or offset 4 bytes to get past that first value. To get to this sort of position 2, if we think of traditional indexing, I have to go 4 bytes, 8 bytes to get to it. This position 3, they're 4 bytes apiece, so I have to move over 4 bytes, 8 bytes, 12 bytes to get to 99,140. Yes, so what we think of in high level, well, so so that one kid points out that the index is actually a number of bytes, and that's correct. We're spoiled in a way by high-level languages because they already do the math for us. High-level languages compute how big each element is for us and automatically scale. But when we're doing assembly, we have to manually scale to get to the elements that we want based on our knowledge of how big each element is. All right, so there they all are, intact, moving over 4 bytes at a time. So I'm going to convert this into a loop now. So the way I would do it, there's a couple of ways we could do it. So this is going to feel weird at first. For do end for, and then let me steal one of these as a template. So this thing in the square brackets is a number of bytes. You can hard code the number of bytes, or you can use a register to represent the computed number of bytes as the byte offset. The weird thing is that the offset is in bytes, but it has to be stored in a 32-bit register because it's a memory access operation. So that's going to feel weird at first. But let me code this up so we could do it in a loop instead. So what I'm doing here is I'm setting up, and this thing is about to become meaningless. So I'm actually going to use the loop. Well, let's do it. Let's be a little bit less cruel to ourselves to start. So let's do it this way, and then we'll do it kind of a different way and see what it feels like. So yeah, Emberwolf says that a function could kind of do some of this work for us, and you're exactly right, Emberwolf. We will want functions to kind of offload the calculation work into an algorithm. So that's kind of what I'm starting to build up here, is an algorithm to get through an array by computing the byte offsets for us. So let's do this. Let's move 0 to EAX. So EAX is our byte offset. And then we'll use CL as a counter just to be cute. CL less than 5, that's the size of our array, and then we will increment CL. So CL, I did CL entirely for the purposes of doing a little output with the high-level style index. So it'll be item 0, item 1. In fact, let's just do it that way. Item number So I'll use CL. I'm going to do this process 5 times. I'm going to use EAX for the byte offset. Why EAX and not something else? Because it's a memory access and it has to be a 32-bit register. So this is a weird thing about x86 assembly. The register being used to handle memory accesses has to be a 32-bit register. But the offset value itself is we're going to be managing it as a number of bytes that we want to offset, which just feels a little bit weird. So we'll start at the 0-byte offset, and then each pass through the loop, we will move it over 4. So does everyone understand? Hopefully everyone understands why I'm adding 4 to my byte offset each time. So why is this value 4 and not 2 or 1? That's a hard one. So that's correct, Druid. It's 4 because I am looping a 4-byte per element array. So that's why I am incrementing, adding 4 to my byte offset on each pass. So I start at 0, it'll move up to 4, 8, 12, 16, and then it'll stop because I'm only going to do this 5 times anyway. So we're going to get the same result, but I used the counter just to make the output look a little bit nicer. So there's my values as I expected them to be. So this is a little bit better because if I were to change this to some other size, then all I have to do is change the loop control and I'm in business. In fact, I could do this. And now I don't even have to memorize it anymore. I'll just change these. If these things change, they change. The code doesn't have to change. Unless this becomes something other than int32. Okay, so we compute these offsets as a number of bytes. We start at the base, which is what the name of the array itself represents, and then we offset a number of bytes. This thing taken together, by the way, the base address, in addition to a byte offset, is called an effective address. I don't know why, but that's what it's called, is an effective address. So the effective address gives you that one piece of data from the array. The base address tells you where the array begins in memory. So there's that one kid asked, can you not use I in the for loops for x86? Yeah, so Emberwolf, you're correct. I'm using the CL as the I. If I wanted to use an I, well, I'll show you what the problem is. So let's just say I made an I up here, which is what I'd need to do. So I could move 0 to I, but now I immediately can't do this because I can't do memory-to-memory comparisons. So the utility of the I kind of immediately gets canceled out if I need to do something like have a loop control variable that I want to compare against. So yeah, it's a lot of stuff to keep straight in one's head. It's a good question, though. You should totally ask those kinds of questions because we want to know the answer to them because they can be interesting. Okay, so there's that one. Okay, let's look at, so this is indexed addressing. I'm going to do it in another way, though, where I'm basically, let me go above that. So let's do, so this is indexed addressing using the array name. Let's do another one where instead we do indexed addressing using the array address. All right, so now we're going to do it different. we are going to use the address of the array so that we can see what it looks like. This would be the case if we had a dynamic array or something made dynamically. We might only have its address. I should move it somewhere. Okay, so let's do the same process, but see what it looks like if we don't use the array name itself, but instead we use the address of the array, which is its base address. So EAX, obtain the base address. Two ways to do this. Yeah, I'll go ahead and rewrite it. I was going to borrow it from myself, but I'll just rewrite it. In fact, yeah, okay. So do in4. Let me get one of these things. Okay, so funnily enough, if we remove the reference to numbers, now we're left with just using the address. But the other thing that happens if we remove the array name is that HLA no longer knows what data type to apply. So if we're going to access, which we are, going to access the elements of the array only through the address and not using the hack of the array name itself, which is really just an assist for the data type, then we're going to have to typecast it. So now instead of kind of thinking of an offset, which was 0, 4, 12, 16, now we're literally taking the array. Let's put its address just for fun. So now we're literally just using the address in memory without the assist of the array name itself. So notice I'm not using EAX anymore to represent the byte offset. I am using EAX to represent literally the memory address I want to access. Add 1. So it'll still be add 4. So it's a good question, Ember Wolf. But the address of the first element is the same as the address of the array itself. And then the address of each successive element is 4 over. So instead of using the array name and a byte offset, we're going to literally use the array address and then just shift the address itself over and access memory directly without the assist of the array and an offset. So I'm no longer even kind of, this is almost, you could say, in fact, I should call it that. It's indirect addressing because I'm no longer using the assist of the array, which is kind of weird. But we'll see it because I printed the address. So I'm not using byte offsets now. I'm literally moving the address across memory to get each element. So I get the base of the array, which the base address gives me the actual first element anyway, when I tell it that I want int32 from there. And then I move it over 4, move it over 4, move it over 4, move it over 4. So no longer a byte offset, but instead the literal address in RAM of that value in memory. So this is really, I guess, better described as indirect addressing to get at the elements of an array starting at the base address. The addresses are 4 over because each element is 4 bytes across from the last one. So that's a good question, Ember Wolf. So how do I know each address of each element is 4 bytes, directly 4 bytes over from the last one? And that's the way that static arrays are allocated in high-level programming and HLA. When you declare a static array, you are getting sequential memory. All of the elements are lined up one next to another in memory. which is one of the reasons why arrays are so performant. Arrays are fast and they are efficient, in large part because literally the entire contents of the array are in sequential memory. If they weren't in sequential memory, instead the pieces of the array were all over memory, then accessing them would take a lot more work for the processor to do. But because they're allocated in sequential memory, we can literally just offset from the last one to the next one in memory, which is also true for the indexed addressing. The reason why we like arrays is because they're efficient this way. All we have to do is go to an address and then shift over some, and we don't have to go looking around for the next element. It's literally right next door. I agree. So that one kid points out that it's kind of it's a trip to kind of throw the array out and still access its contents simply because I have a memory address, and that I know that if I have the location of the first element of the array, knowing that all of the rest of the elements are in sequential memory, then all I have to do is shift the address over to get to the next element. Well, so yes, so Druid asks if we'll go over scaling. We will do that. That's another way to do it. So yes, we will definitely do that. Okay, so we don't even need the array other than to mark the starting location in memory, and at that point we're kind of free to just use indirect addressing to get at the elements. So yeah, that's true. Ember Wolf points out in chat that the addresses are associated with size, and that's true, especially when you're talking about sequential memory, because you have to know that if you have an int32 and an int32 and an int32 and an int32 in sequential memory, that each one of those is 4 bytes over in memory from the last one. So that's true. Their addresses are associated with how much memory, the size that they are consuming. Okay, so there is indirect addressing. Now let's do scaled addressing, which will be a little bit more familiar to people. Oh, actually, let me show. I'm going to show you all of the variants here while we're sitting here. So let's do. Yeah, I'll just redo it. So so that was really indirect addressing. Let's do indexed addressing using the array address, so that we can actually use the address and a byte offset in syntax. So we're going to use a similar setup here. So EAX is the base address. It's just how I should have said that before, is the base address. All right, I'm going to write this. How do I want to do this? Yeah, let's do this. Steal the code. Do I want the address? No, I don't care about that. All right, so I interrupted myself with that indirect one, but let's go back and do, let's access it without. So now let's go back to the index. So here's another way that you can do this. So you can use in HLA kind of something similar to high-level array programming, except for you have to understand that we don't use what we like to think of as indexes. They're byte offsets. We can actually use indirect addressing itself by loading up the base address and then shifting the address over, matching the size of each element when we shift it. Now let's do this one where we will take the base and we will add an offset. So this is x86 assembly syntax. The absence of the array name itself means that HLA can't type it. So we're going to have to type it. So this is another way of doing array indexed addressing, where we don't move the base anymore. We just add an offset. Now notice they have to be 32 bits. The base address has to be 32 bits and the computed byte offset has to be 32 bits. But this is another way that we can get at the elements of an array. So I'm back to doing byte offset. In fact, let's change this to say byte offset. So the base address is now not going to change in this style. We're just going to move the, so EBX is the byte offset. Still going to do it 5 times. I'm still going to use, byte offset is going to be an uns32 EBX. Crazy. Yes, so Emberwolf asks, is that plus sign allowed in other places? And the answer is no. The plus sign is allowed in x86 assembly for this purpose of expressing, of doing memory accesses, addressing mode. So this symbol, the plus symbol here, is part of x86 addressing, indexed addressing mode. So we can use the plus when we have a base address and we want to add a byte offset to it. So the base will never change, but the byte offset will. So it'll be the base of numbers plus 0 and then plus 4 and then plus 8. And then I'm gonna, in a second, change the size of the array back down and we'll see what that affects. So there they all are. Everybody's happy. Okay, so hopefully you guys can follow me here. Let me comment this out and make a smaller one, and let's see what making a smaller one changes. So I'm going to go to int 16. I'll keep it at 5 just in case. And then we'll go back to the 110, 120, 130, 140, 150. Okay, so study this for a second. I have an int 16 array now, 2 bytes a pop. So the question is, for this now array that I want, this int 16 array, kind of use the line numbers as a reference. So what has to change in my loop now to account for the fact that each element is only 2 bytes and not 4? Line 24 is exactly right. So Emberwolf is dead on. It is line 24 that now has to have an adjustment. And what is the adjustment? Add 2. Nice one, Druid. Add 2. So still needs to be a 32-bit because we're using it as part of a memory access, but we will alter it to do 2 bytes of byte offset a pop, which will get us not. What did I do wrong? 0, 5. Oh, oops. Forgot to change the typecast, so it was all crazy. So that's important because HLA needs to know how much data to look at and how to interpret it. So the int 16 tells HLA to look at 2 bytes at this address and type it as a signed integer. Okay, so that ought to fix that giant looking problem. Yeah, so now we're back to what it should be. So it's a lot to keep straight in one's head when we're grateful for doing C++ programming, because you simply use 0, 1, 2, 3, and all of the magic of computing the byte offsets is done for you by the language. But at the assembly level, that actually has to be manually done. Okay, so now let's do the last one, which is very cool looking, which is, I'm going to go up to the top again, scaled, indexed addressing. So still going to use EAX for the base. And then I'm going to do move 0 to CL, CL less than size. Why I wasn't doing that consistently, I don't know. Size. Inc CL. I think I got one extra. Yeah, let me cheat and grab one of these. Okay, so here's another way you can do it. And then this will allow us to refactor the code a little bit as well. So how does it know the size? We have to tell it. So it's a good question, Emberwolf, who asks, how does the software and the processor know the size? It doesn't. We have to tell it. So unless we have a declared array name that HLA remembers the size associated with it, we have to use typecasting and communicate that ourselves. Kind of crazy. Okay, so let's do scaled indexed addressing, which is kind of exciting. And I'm going to change some things because I can now use, with scaled index addressing, I can actually use the for loop counter as part of my addressing scheme. I may not understand. Oh, this size right here, that's a variable. Maybe that's what you're asking, Emberwolf. I declared a variable for that. So it doesn't know the size. Okay, yeah. So I may have forgotten to tell you guys I did that. And I forgot to use it consistently. So yeah, I added this variable to represent the size as a convenience. So yeah, I forgot about it too. So that's there as a convenience. Now there's a problem here because I want to compare it to ECX. So I'm going to have to change it to be an UNS32 for this to work. The sizes have to match anywhere. So notice that I've changed the for loop because we're about to do scaled indexed addressing. So why did I change the for loop? Because scaled index addressing brings us just ever so slightly closer to what you are used to, which is you are used to taking the base address and using an index. So ECX will go 0, 1, 2, 3, 4. But the magic of high-level languages is that they're automatically doing this part for you. They are applying a scaling factor on the index for you. So this is scaled index addressing. It's kind of the sexiest thing, one of the sexier things we do in the class, because it's just kind of cool, and it no one who's not done assembly would even know what to make of this code, probably. So what does this thing say? Go to the base address, offset by this amount. So when ECX is 0 and we scale by 2, we get 0 bytes. When ECX is 1 and we scale by 2, we get 2 bytes. So 0, 2. When ECX is 2 and we scale by 2 bytes, we get 4. So scaled index addressing is a little bit more like what we're accustomed to, even though it's happening where we can't see it in a language like Go or C++. We apply the index as we understand it, 0, 1, 2, 3, 4, and then we scale the index to match the data size. The data type. I still need to typecast it so that HLA knows what to do ultimately. Take 2 bytes and interpret it as an int16. So this is what scaled indexed addressing looks like. Notice still the square brackets, which means we're still doing a memory access. So go to this base and then offset by this scaled amount of bytes. So that should just yield to us the same values, so we're all happy with that. So I'm going to make another change. So let's put the 32-bit one back. So I'm going to restore the 32-bit array and then figure out what I have to update in my loop to make it work for that 32-bit array. In fact, I'll highlight the section because it's probably pretty obvious where these changes need to be. So what changes do I have to make in that section of line 15 to make this loop work for the int32 array? Okay, so the scale is 4 bytes a pop. That's true. Yeah, so Emberwolf points out that we can now, like, oh, all of a sudden we can do addition and multiplication like we're used to. And that's true. x86 processor supports this way of doing this addressing mode, which means it supports these operators for this specific application. Typecast to int32, good one. So a good one is Nom and Emberwolf. Typecast int32. We now have 4-byte scale, and now I'm ready to roll. And there's my my 32, my int32 array. So this is the one that I like the best of these, as long as I kind of train myself to recognize what's going on here. The first element must be a base address, and it won't change when you're doing scaled indexed addressing. You have the same base over and over and over again. What changes is the index. The scale won't change when you are going across an array. So it's a 4-byte per element array. ECX is doing the traditional index counting, 0, 1, 2, 3, 4. And then each of those indexes is being scaled to match the number of bytes per element in the array, which is pretty cool. All right, so there's scaled index addressing. We did some indirect just by moving the address itself around. Let's put that one at the bottom. I like that one down here. And then the last one is scaled indexed addressing. So if you're asking yourself which one of these should I use, it's either the one that the instructions state that you should use so that we practice them all, but on your own project, you use the addressing mode for getting at your array data that you feel comfortable with and that works for your situation. I personally find this scaled indexed addressing mode to be the most flexible one in terms of writing the code around it. You give me an array, you tell me what type of data is in it and the size, and I can handle the rest. So that's a lot more information than we need in a language like C++, where if we have an array, well, let's go to the C language instead. In the C language, I need to know the name of the array and the number of elements in it, even though I could actually compute those. The name of the array, the number of elements in it, and then I don't have to worry about anything else because the scaling part is done by the language. C++ is the same unless you're using a library array, in which case you don't even need to know the size because the library array has a function for that. We just need to know the array, and then we can compute its size, and then the scaling happens automatically. So at the assembly level, and something that HLA will partially force us to do, we need to know the array name or its base address. We need one of those things. We need to know the type of data that's in it so that we know what scaling factor to use. And then we need to know the size so that we know how many things to go looking for. We can capture that as a function, which we're doing on the lab, but I'll go ahead and write one from scratch just so you can see how I put it together. So if we wanted to make a function that could print, let's just say, I'm just going to go for glory here and say any kind of uns8, uns16, uns32, int8, int16, int32. Could I make one procedure that has the logic in it to print any of those types of array? Yes, if I know the address of the array, the size of the array, and the kind of data that's in it, then I have everything that I need. So here's what that would look like. I will say print array. So I need an address, which in HLA we can represent as a double word, a 32-bit raw data value is appropriate for representing the addresses of arrays. I need to know the size. I'm going to use uns32. And the reason why you're going to see that a lot when we talk about addressing modes is because addressing things are done in 32-bit types. So sometimes we're going to use 32 bits where it seems like we don't necessarily need to in terms of the quantities being represented. But if you see a 32-bit something that doesn't seem necessary, like it's too big for the quantities that we're dealing in, there's a good chance it's because it makes it easier to do memory accessing work because that has to be done in 32 bits. So I need to know the size and I need to know the type. I'll call it the data type. The data type, I can do an uns8 here because I only have 6 data types to contend with. Okay, so begin print array, end print array. So what would this look like? First thing we do is we'd move this address into EAX. And in fact, I'm going to use the stack just to be a good programmer. So the address has already been extracted somewhere and passed to this function. So I don't need to extract an address. That just is an address value. So I'm going to move it to EAX because I can't use addresses unless they are in registers. Just a fact of life in x86 assembly. I got to get that address in a register for it to be usable. Fire up a loop. Going to do 32-bit things because I want to do scaled indexed addressing. ECX less than the size. Here's why I wanted the size to be a 32-bit something so that I could use ECX in my loop and compare ECX to the size. They have to be the same 32 bits, so that's why the parameter is 32 bits. And then I increment ECX. So we've just seen a whole bunch of examples of this thing. All right, so what do I do in the loop? So in the loop is where I have to determine which of the data types that I want to print do I have so that I know scaling factors and that kind of stuff. So the way I would do it, just to keep life from not being overly complex, even though this is complicated looking. So if the data type equals a 1, then, and let's just have a little coding scheme. So one's 8.